Hello. Dum-de-dum-de-dum. Have a doozy of a lesson for you guys today. A real doozy. Hola. I'm going to wait for 2 more people and then I'll get started. One more. Okay, no one else is coming, so I guess I'm going to start. Hello, everyone. So today we are going to be discussing so this is CHL, February 11th, period 7. And today's lesson is about the electric field due to continuum charge distributions. Okay, so calculator here. So earlier on, we were talking about discrete charge distributions. So if you want to find the electric field at some point P, and you have a discrete charge distribution, you would basically take the electric field created by each of those individual charges, and you would add them up, and that would be your electric field at the point P. If you have a continuous distribution of charge, what is the difference between discrete and continuous? Basically, if it's continuous, then you have some extended object that has charge throughout it, okay? So you can't really identify the charges there or there or there. Because in order to do a sum, you have to say, oh, the charge is there, and then the next charge is there, and then the next charge is there. But if it's continuous, there's so many little charges that you can't do that. And so in that case, you have to do an integral, okay? And you have to add up dE. So what do I mean by dE? So dE is an infinitesimal electric field, okay? That's created by part of the object, okay? So what this says is to get the total electric field, what we're going to do is we are going to add up all the infinitesimal electric fields. Okay, so when you're adding up things that are infinitesimal, it's not a sum, it's an integral. And in fact, the integral sign is an extended s for sum. Okay, so this is how we're going to be calculating the electric field in the next few lessons as an integral. So what do I mean by dE? Okay, this is basically an infinitesimal electric field, so an infinitesimal amount of E, and it's equal to it's just Coulomb's law, right? It's K dq over r squared times a direction vector. So the infinitesimal amount of electric field is due to an infinitesimal amount of charge. Okay. R squared. So R is how far away dq is. Okay. And then dv is the appropriate direction vector. All right. So this is basically Coulomb's law in infinitesimal form. Okay. So what we're going to do is we're going to plug that in for dE and do the integral. All right. Now the magnitude of dE, which I will oftentimes just write it as dE without the arrow over the top. To do that, we would just take away the direction vector because this is just a unit vector, right? So the magnitude of the infinitesimal electric field is K dq over r squared. Sometimes we will want the x component of the infinitesimal electric field, and that's going to be dE times a trig function. Okay, and we'll see how that works in a second. And then the y component of the infinitesimal electric field is also dE, but times a different trig function. So infinitesimal electric fields work just like regular vectors. Okay, so if this is your infinitesimal electric field and it has a size dE, then this is the x component of your infinitesimal electric field. This is the y component of your infinitesimal electric field. So what we're going to be doing today is we're going to be finding an expression for dE, and then we're going to be integrating it, so adding up all those infinitesimal electric fields to get the total electric field at some point. Okay? Now here's the good thing. The AP Physics C exam is a pen and paper exam, okay? And when you do these kinds of problems, you set up the problem, and then you'll see in a second, we'll get to the point where we have to do this integral. And I would say 99% of the time, that integral is impossible to do without a calculator or without a computer. Okay, so so basically, the good thing is there are few examples you can do without a computer. Okay, so if you want to master this, really all you have to do is you have to master those few examples that you can do without a computer. And there's literally like 4 of them, okay, that have the amount of math required is within what a human can do and not going over to a computer. Okay, so basically what I'm going to be doing in the next couple lessons is we're going to be going over what are those 4 examples, okay, and trying to get familiar with them. So the first example I want to talk about is a semi-infinite line of charge with a constant linear charge density lambda. So you might remember that lambda I see there's a question about the HL exam, and I have something to say about the HL exam once we go to the Zoom room, okay? Lambda in mechanics was used as the linear mass density, but really in general, lambda is just used for any linear quantity, its density in a linear sense, okay? So when I say that it has a linear charge density of lambda, I mean that dq dx is equal to lambda, which in this case is equal to a constant. It could be a function of x, but in this case it's not. Okay? So let me draw a picture of what we have here. We have the origin. Okay? And then when I say semi-infinite, I mean that this line of charge starts at x equals a. Here's the origin is at x equals 0, right? Starts at x equals a, and it goes out all the way to infinity. Okay, so it's semi-infinite. An infinite line of charge would be infinity and negative infinity. Okay, and so what we want to do is we want to calculate what is the electric field vector at the origin. Okay, so whenever we are doing these problems where we have a continuum charge distribution, what we want to do is we want to imagine a little tiny piece of this semi-infinite line of charge. So let's consider just any piece. We'll just pick a piece, this little piece from here to here, an infinitesimal piece of charge. And it is at location x. So x would obviously have to be greater than a in order for it to be within this semi-infinite line of charge. And it has a total amount of charge dq. So, and it has a width dx. Okay? So, if we think about this little piece of charge, and we'll assume it's positive, this little piece of charge creates an electric field that points away from it. Okay? So if we're at the origin and we want to run away from this little piece of charge, that little piece of charge is going to create a little electric field that goes in that direction, because that is the direction that is away from the little tiny piece of charge. Okay, so what that means is that dE points in the negative I hat direction. Okay, so notice how our dE has a direction vector. So that means that our direction vector is negative I. Okay. Furthermore, we need to figure out what is dq. And so if we take the definition of linear charge density and we multiply both sides by dx, what we're going to get is dq equals lambda dx. All right. And then what's the other part of dE? So we're basically looking at dE and we're trying to fill in each of these components. K is a constant. We wrote out what dq is. We figured out what the direction vector is. Now we got to figure out how far away is dq from the origin. Okay. dq is at location x. The origin is at location 0. So what is the distance between here and here? That distance is x. Okay, so little r is equal to x. So now we have all that information. So we can say what dE is. So dE is k dq over r squared times a direction vector. Okay, so we know that dq is lambda dx. We know that the distance of dq from the origin is just x. So when I divide by r squared, I'm going to divide by x squared. And we know that our direction vector is in the negative I direction. All right. So I'm just going to write that one more time, just factoring out some stuff. So I have k lambda, negative k lambda I hat times dx over x squared. So now, to get my total electric field at the origin, I've got to integrate the infinitesimal electric fields due to all the infinitesimal pieces of charge within this semi-infinite line. So I'm going to integrate negative k lambda I hat times dx over x squared. Okay. And so this is going to be a definite integral. So I have to figure out what are my limits of integration. And I can see that x is describing the location of an infinitesimal piece of charge. So I can see that there are infinitesimal pieces of charge from x equals a all the way out to infinity. So this goes from a to infinity are my limits of integration. All right. So now what I can do is I can factor out what is, so my integration variable is x. So anything that doesn't depend on x, I can factor out. So I can factor out k out, I can factor out lambda out, and I can factor out I. Why is that? Because if I thought about a different piece of charge that's also along the line, so maybe this is dq1 at x1, maybe this is dq2 at x2, I can see that both of these infinitesimal pieces of charge create an electric field that points to the left. Okay, so no matter which infinitesimal piece of charge I'm looking at, it's always going to create an electric field in the negative I direction. So that's a constant. So I can factor it out. So what I have is k lambda I hat times the integral of dx over x squared from negative dx over x squared from a to infinity. All right. So at this point, the physics is done. The physics is done at this point. So the rest of this is just the mathematics of evaluating this integral. Okay? So I don't really care how you evaluate this integral. You could evaluate it with a calculator. You could evaluate it with Wolfram alpha. It doesn't matter to me. What matters to me is that you can get to this point, because this is the point where physics stops and math begins. And I care more about physics, that you understand the physics, than I care about you understanding the math. So if you don't know how to do integrals, you just take this integral and plug it right into your calculator, and it'll just go and give you a nice answer. Okay? For completeness, I am going to show how to do the integrals in today's lesson. So the integral of negative dx over x squared is 1 over x. Okay, and because this integral is from a to infinity, I'm going to evaluate this at infinity and at a. So this is going to be equal to 1 over infinity minus 1 over a. 1 over infinity is 0, because if you take a pie and you divide it into an infinite number of slices, no one gets anything. So the value of this integral is negative 1 over a. Okay, so I plug that in here for this integral, and I get minus k lambda over a times I hat is the electric field at the origin in this case. Should also just do a sanity check. This equation makes a lot of sense because the electric field points in the correct direction. If I take this semi-infinite line of charge and I move it further away, it's obviously not going to make as much of an electric field at the origin. So I can see that as A increases, the electric field gets smaller in size. Furthermore, if I increase the amount of charge density, that should create a bigger electric field at the origin, and I can see that lambda is on the numerator. So more charge density means more electric field. All right? So let's do another example. So we're just doing examples for the rest of the class period. So in this example, we have the origin is right here. And we have a point P that is directly above the origin. It's a distance y above the origin. Okay, so this P is at coordinates 0, y. Good question. There's a question in the chat. How do you have infinity as a bound of integration? So if you have infinity as a bound of integration, it's what's called an improper integral. It's improper. And basically what an improper integral means is you do the integral from, like, say, a to b, and then you solve the integral, and then once you've solved the integral, you take the limit as b goes to infinity of the expression. So that's called an improper integral. It's a thing. All right, so here's the point P. And then we have a line of charge that extends from x equals a to, all the way over here, to x equals b. along the x-axis, and the linear charge density here is constant. Again, lambda doesn't have to be constant. Lambda could depend on x. It makes the integrals tougher, but because if lambda is not a constant, you can't factor it out. So it adds more stuff to the integral. So now what we want to do is we want to just take a little slice of this, which is called dq, and it is at coordinate x comma 0. Okay, so that's where it's located at. And so this little electric field, okay, creates or this little infinitesimal piece of charge creates an electric field that points directly away from it. So it's going to create a dE that points in that direction. Okay. Now, I didn't even say what we want to calculate here. We want to calculate the x coordinate, or the x component of the electric field at P. So how are we going to calculate the x component of the electric field? Well, we're going to integrate dE, but we're only going to integrate the x components of them. Okay? Because I want the x component. The x component of the total electric field at point P is the sum of the electric field of the x components of all of those electric fields. Okay. So let's go ahead and figure out what is so dE is going to be k dq over r squared. So we got to figure out what is dq. Well, dq is lambda dx, just like last time. Okay. What is r squared? R squared is the distance from this dq to the point P where I'm measuring the electric field. So that distance right here, well, I know that this distance is x. From the origin to dq is x. And this distance is y, and this is a right triangle. So this is square root of x squared plus y squared. Okay, so that is r. So when I square that, I get this without the square root. All right. Now, let's just look at, I'm going to draw this bigger here. So here's dE. Here's dE sub x. Here's dE sub y, the x component of the infinitesimal electric field and the y component of the infinitesimal electric field. And let's call this angle theta. Okay. So one of the things I can see here, if that angle is defined as theta, then dE sub x is going to be dE times sine of theta times -1. Why? Because this electric field is pointed to the left. It's more to the left than it is to the right. Okay? So I got to multiply by sine theta. Remember how I said that if you get a component of the infinitesimal electric field, you multiply it by a trig function. Okay? So, anyways, now here's something kind of interesting, is that this is a straight line, and this is a straight line, and this is your angle theta. So that means that this is also the angle theta. So we're going to use this triangle to get the sine of theta, and I can see it has an opposite of x and a hypotenuse of square root of x squared plus y squared. So that means that my sine of theta is x over square root of x squared plus y squared. Okay, so now I have an expression for dE, and I have an expression for sine theta. So I can plug those in. So I get dEx, x component of the infinitesimal electric field is minus k lambda dx over x squared plus y squared times x over square root of x squared plus y squared. Okay, now if I want, I can take these two together. So this is kind of like z, and this is z to the 1/2. So I'm going to combine them. I get the 3/2 power. So my dE sub x is minus k lambda times x dx over x squared plus y squared to the 3/2. All right. So now I'm going to take that and I'm going to plug it into my integral. K, lambda, and -1 are all constants, so I'm going to factor those out. So I have minus k lambda factored out of the integral, and then I have the integral of x dx over x squared plus y squared to the 3/2. So what are my limits of integration? The limits of integration is the extent of the line of charge. So the line of charge goes from x equals a to x equals b. So my integral is from a to b. So we got to solve this integral. So as I said, at this point, the physics is done, and now it's just math. And for completeness, I'm going to show how to do the math. This is a u substitution problem. So you're going to let u equal x squared plus y squared. And then du, so y is just a constant, so du is 2x dx. So if you can see, right here I have du over 2, and right here I have u to the 3/2. Okay? And so you do the integral, and that's going to give you k lambda over x squared plus y squared to the 1/2 power, evaluated from a to b, because it's a definite integral. So you can double check it by taking the derivative of this. With the integral is over x, so I have to take the derivative with respect to x. Taking the derivative with respect to x is going to bring out a -1/2 and reduce the power to -3/2. Okay, and then when I do the chain rule and take the derivative of the inside, it's going to give me 2x. So I have -1/2 times 2x. So the 2 and the 1/2 cancel out, and I just get -x. All right, so it works out. So now doing the evaluation, I plug in b for x, and then I plug in a for x, and I subtract them. So you get k lambda over b squared plus y squared to the 1/2 minus k lambda over a squared plus y squared to the 1/2. And that is the electric field, the x component of the electric field at point P. Boom. All right. Now, one thing that's kind of fun about this, I didn't do this last class period, but what would we want to set b equal? Type it into the chat if you know. What would we want to set b equal to? And what would we want to set y equal to in order to reproduce the same problem that we just did? This one. Type it in the chat if you know. So we want to make this problem identical to this problem. What do we have to set b equal to, and what do we have to set y equal to? So we get the previous problem if, I guess no one wants to answer. So we get, oh, okay, very good. Yeah. If y equals 0, so y equals 0 will mean that this point is down here at the origin. And then the other side of this charge distribution has to go all the way out to infinity. So b equals infinity. So if we plug in b equals infinity here, this term drops out because we have infinity in the denominator. And then if we plug in y equals 0, then this term becomes 0, and we just get a squared to the 1/2. A squared to the 1/2 is just a, and we get minus k lambda over a. It's the same thing. Okay, I think that's neat. So, now we're going to do one more example here. And what if we have a uniform semicircle of total charge Q and radius R. A uniform semicircle of total charge Q and radius R. So what does that look like? Well, we have a semicircle. Okay. And what I want to know is, what is the electric field at the origin? Okay. So now here's a little trick. If you have a circle or a portion of a circle, your integration variable is going to be an angle. Okay? Because circles are just, you can locate where you are in a circle best using an angle. So I'm going to call this point theta equals 0. Then this point would be theta equals pi over 2. Okay? And this point right here on the other side would be theta equals minus pi over 2. All right? So now what I'm going to do is I'm just going to consider a little piece of charge on the circle. So this is dq. All right? And it is at an angle theta. All right? So dq creates a little bit of electric field that points away from it, so that would be in this direction. Okay, so this is our dE. And notice how we have the same business of these two angles being the same, because this is a straight line and that's a straight line, so these are whatever you call them. Someone type it in the chat if you remember what the relationship between those two is called. I can't remember. So this would be dEy, and this would be dEx. So, all right. So notice, now here's the thing. By symmetry, E points down. Okay? Why is that? Well, if, even though this infinitesimal piece of charge creates an electric field that points away from it, this does not point down. If we sum up all of these infinitesimal points of charge, we're going to get a total result that points downward. Because if I take this semicircle and I flip it like this, it's the same distribution of charge. It's the same on both sides. All right? So what that means is that, so we're going to get a, so the electric field has to respect that symmetry. Whatever direction the electric field points has to be the same if we flip it that way. So that means it has to point up and down, okay? So when I calculate the electric field at the origin, I know it's going to point in the negative j hat direction. That's going to be my direction vector. And I'm only going to integrate the y components, because those are the only components that are going to matter, okay? So how do I get the y component? Well, I can see that the y component is adjacent to the angle, so that is cosine. So I have the integral of dE cosine of theta. All right. So now I have to figure out what is dE. Well, if I look at this infinitesimal piece of charge, dq, it is a distance big R from the origin. And that doesn't matter where we are, which piece of charge we're talking about, right? Because if I take another piece of charge here, it is still a distance big R from the origin. That's because it's a semicircle, okay? So what I have is that little r is equal to big R, which is equal to a constant. So in that expression for dE, the little r is going to be a constant. Then I have to figure out what is dq. Because the integration variable is an angle, I'm not going to do dq dx. I'm going to do dq d theta. Okay? So this is charge per angle. So how much charge do I have? Well, I have a total charge q. And because it's a semicircle, the total amount of angle in a semicircle is pi radians. Like that. Multiplying both sides by d theta, I get that dq is q over pi times d theta. All right? So now I know these two pieces, which is going to allow me to get dE, because dE is k dq over r squared. So this is going to be k times dq, which is q over pi times d theta, over big R squared. Little r and big R is equal to big R in this case. So now I'm going to just collect some terms to simplify. I have k times q over pi r squared times d theta. So this is what I'm going to plug in right here for dE. So I have minus j times the integral of kq over pi r squared d theta times cosine of theta. So now I have to do my limits of integration. We can see that the semicircle goes from minus pi over 2 to plus pi over 2. So that means that my limits are minus pi over 2 to plus pi over 2. And furthermore, anything that doesn't depend on theta I can factor out, which is all of this stuff. So I have minus kq over pi r squared j times the integral of cosine of theta d theta from negative pi over 2 to pi over 2. So in the interest of time, I am not, oh, someone typed in what it's called. It's called vertical angles. They're vertical angles. Thank you. So this is the point at which physics stops and math begins. So this integral, the integral of cosine is sine, and then sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. We subtract those, we get 2. So the value of the integral is 2. So my answer is minus 2 kq over pi r squared times j hat. That is the electric field at the origin. All right. So I have some announcements to make in the Zoom room. So let's go to